I'm going to give you some, for us it's quite exciting, very simple chemical process approach to design nanoparticle and nanostructural particle by just converting our conventional chemical process into this nanoscale system. The name of my talk is hyperstructured polymeric nanomaterials using controlled dispersed condensation purification. You already know about the dispersed polymerization, so I'm not going to go in detail about that, but for that I add this condensation process into this dispersion polymerization. That means you have initiator in water or oil soluble system, and continuous phase you have a water, alcohol, solvent. And discrete phase initially it atom and monomers, now it turns into the polymers. And swollen particle forms, and you need to have some kind of stabilizers to make the droplet or final particles. But for this, we adapt the supercritical fluid as a continuous medium during the reaction period. And then that has a very important role to control the reaction scheme and the structure of the final particles. So I summarize this CDCP in three categories. The one is that it can run the reaction in micro or nanoscale synthesis, because the reaction actually is started in the dispersion or micelle, which you generate in the continuous medium. And to do that, you can add some kind of versatility on this process. And also you can overcome some kind of process limitation we always face during the conventional reaction, just like as solubility control or dispersibility control. And also you can run the reaction, different type of process in one stage, like you can actually, in the first stage you can make the dispersions, and then slowly you can start the reaction, and then if you want to exchange some material in between growing the particle and then outside of your continuous phase, you can do that. And then finally you make the particle, you can just easily separate that particle from the reactant by just control the pressure. So for that, I just suggest one very simple process to verify our concept by doing this CDCP process. Just the general scheme of the simple reaction of condensation reaction, monomer A reacted to monomer B. Now you make the product. So actually we like to have some kind of nanoparticle as a final product. And during this reaction, we choose this kind of general scheme, the general approach to make the condensation polymer. Always you have some kind of byproduct generated during the polymerization. That always some kind of small molecule like as water, ethanol, or alcohols. Sometimes as a salt or unreacted monomer, etc. So compared to the bulk process with our this particle process, always the bulk process is very difficult to separate the byproduct during the bulk, during the reaction in the bulk reactor system, and always requires some kind of higher reaction temperatures. And because of that, it's not easy to make high molecular weight polymers, and also you cannot easily achieve the high degree of polymerizations, and also it's very difficult to control the molecular weight. So now you can convert into this nanoscale dispersion type reaction system. Our suggestion is by controlling some kind of process, by adjusting the solubility of the continuous medium with some materials generated in the particles, you can extract that from the reaction side into the continuous phase. And for that, you can actually increase the degree of polymerization. and also you can achieve the high molecular weight polymers. Basically, that's our goal to achieve, and for that, I'm going to give you the actual result. The one approach is whether we can make the high molecular weight for the carbonate nanoparticle by using that to control this polymerization. And this is just to control the particle size and molecular weight. And the second approach is whether we can control the structure of that nanoparticles by using our process. Finally, whether we can control the morphology of the casting film by using these polyimide materials. So as you know, the supercritical fluid we use here is the carbon dioxide supercritical fluid, and supercritical fluid means once you reach this critical point, that fluid act like liquid-like density and gets like viscosity property, and that has this kind of advantage. Manipulation of the solvent strength by just changing the temperature and pressure. This is the key concept to apply to our system. And this is another advantage by using the supercritical CO2, but I'm not explaining this in detail. Okay, for this, you need to have some kind of stabilizers to make the dispersion in the continuous supercritical fluid. So several choices you can make. The one is the CO2-philic, hydrophilic graft polymer you can use as a stabilizers, or fluorinated or siloxane-based polymers you can use as a stabilizers. And several of them you can choose. And there are some genetic types of surfactants or stabilizer also you can adapt into this kind of system. And or if you are good at the organic chemistry, you can actually synthesize the proper surfactants to create this kind of stabilizer. But anyway, this is a schematic diagram of our approach. In the initial stage, just it has a two-phase supercritical CO2, and that another solvent has all kind of materials you need to run the reactions, and then create this kind of dispersion, just like as suspension or dispersion. You create this by mixing this with add some stabilizers to create this. And the initial size of this dispersion is very important to control the final particle size of your product. And compared to the conventional dispersion system, this one has another functions to control the process of this reaction. That means since you can adjust the solubility power of this supercritical CO2 with the another solvent or another materials generating inside of this particle, either you can create the heterogeneous phase of this dispersion in the initial stage, and then you just simply adjust the temperature and pressure of this continuous medium. Now you turn into this kind of mode. That means now this supercritical CO2 can penetrate into this glowing particle and extract some solvent or some small molecule and take it out into this continuous medium. That means this, once you have a small molecule generated during the polymerization, and easily you can take it out, that small molecule outside of these growing particles. That means you don't have any byproduct inside of these particles. So once you reach the final point, you just simply adjust the pressure of that system, and the final product is just separate out of the reaction. And then total of this continuous system simply recycle. And then you add monomers, and then you can continuously run the reaction. I suggest this is a kind of ideal chemical process for the future. That means the zero discharge process. This is another important factors to make that kind of process possible. So you have to choose the right core solvent to do that kind of job. That means in the initial stage, you need to have some kind of solvent can act as the second solvent to control the solubility between the continuous supercritical CO2. So that means in the initial stage, you use these conditions. The number one is that we choose the heptyl alcohol for our system. That's because this heptyl alcohol solubility changes like at higher temperature and low pressure, like and at this point, is the solubility of this heptyl alcohol in the supercritical fluid is very low. That means you can create the dispersion, heterogeneous system in the continuous supercritical fluid in these state conditions. And reaction, during the reaction, during the reaction, you need to have some kind of solvent or byproduct exchange process. You just simply adjust the pressure, like this number 2 John, just reduce the temperature and increase the pressure. Now the solubility of this heptyl alcohol in the supercritical fluid is very good. That means it acts like some kind of, now that this supercritical fluid can penetrate into the growing polymer particles, now that the growing polymer particle already has enough molecular weight, can stay inside of the particle, and then it's not a break. That droplet is now turned into the polymer particles. That means you don't need to worry about the solubility of that heptyl alcohol and the supercritical fluid. And then during the reaction, just adjust the pH, temperature and pressure. Now the mode is moved into the extraction stages. So this is the process we apply to make that kind of particles. Okay, so if you remember my first part of presentation, so we just simply choose this polycarbonate system to make nano size polycarbonate with high molecular weight, because this one during the reaction it makes the panel as a side product. So whether you can actually extract this panel from the growing particles, that will determine whether you can make the high molecular weight of polycarbonate particle in the end. So we choose 3 different processes to verify our concept. The one is the process, the polymerization, dispersion polymerization without exchanging process. And the number 2 process is partial extraction process. The number 3 process is the continuous exchange process. So this one is whether actually we can extract the side, this byproduct from the growing particles. So this is the FDIL analysis of this final, the extracted byproduct, this panel and heptyl alcohol. This one shows the panel and heptyl alcohol, and this is the pure panel, and this is the pure heptyl alcohol. So we verify from this analysis, we confirm that our extracted byproduct actually has a panel and heptyl alcohols.
And this is the FTIR analysis of our final polycarbonate particles. And this is the result of that. And not only we managed to make the nano-sized polycarbonate particle by using our very simple concept, but also we can actually control the size and the size distribution of that polycarbonate by adjusting the process. The process means to control the pressure and temperature and also control the extraction mode. So this one is the partial extraction mode of process, and this is continuous extraction mode. And the final particle is this one is around 100 with quite broad size distribution. And this one is continuous extraction mode, gives us about 45 nanometer with quite narrow size distribution. And furthermore, the most important evidence of this process is the molecular weight of that. So here, and also this one shows the effect of the different type of surfactants can do the same kind of job to control the final particle size. This one is using Privalock type. This is just generic type, the pronic system. And this one gives about 50 nanometer size. And this one is the fluorosurfactants. And this one, you already realize that this one is a lot better than this one for our system. And because of that, the final particle size of this is about 30 nanos, and this one is about 20 nanos. And this is somewhat, we are quite excited about our result. It's the final molecular weight of the particles. So normally, polycarbonate average molecular weight of the polycarbonate is about 30 to 50,000 in that range. And here we achieved 10 times higher molecular weight than just conventional that post-scan melt process, the conventional polycarbonate. This one is about 300,000 molecular weight of that. So that means just simply apply the chemical process into this kind of particle manufacturing system, you can actually achieve very tremendous different type of result. And next one, I'm going to show you that not only control the size and molecular weight of the final nanoparticle, but also by using that supercritical system, you can actually generate very narrow pore developed nanoparticles. Just one step. For that, we choose this standard network form polymerization using phenolic double oligomers, and for fluoride now add acid catalyst, you make a crystalline gel, and this we call this a gel gel, and then you exchange that uncrystalline part that always combined with water. So you have to exchange water with acetone, and then extract the acetone by using the supercritical fluid. You finally make this kind of aerogel. So you may be familiar with how to make the aerogel. And our process is to. This one is our approach. This is the conventional way of making the aerogel particles. Normally it takes about 3 to 4 days. And also it's very tedious because in the first stage you have to make the aerogel by doing this reaction. And second stage, because of the density difference, you have to exchange water in the aerogel with acetone, and then extract that acetone using supercritical fluid to make the porous particle or porous materials. But we approached this one-stage process by just applying our concept to change pressure and temperature to control the solubility of that system. Because in the first part, I already told you that just control the solubility of the solvent in the supercritical fluid. In the first stage, you can make some kind of dispersion, and then during the polymerization, just adjusting the solubility between the solvent and the supercritical fluid, you can actually make the exchange mode. And then finally, you create the particle in this one stage process. And this is the result. Changing amount of solid content doesn't have much effect on the final particle size of the system. And anyway, this one we make about, let me see, about 2 micron to the 4 micron particle size. Next one. And we also apply some different type of stabilizers. And stabilizer also doesn't do much work on in the change the final particle size. And this one is very important. And the first approach is we make the 2.2 micron, and then we change the subsequent system. Now we end up with making about 50 nanometer final particle size. This is not just the particle itself. And the next one, it has a pore developed. All of these particles. This is the evidence. This is the pore size of that is about 1 to 5 nanometer. We don't know exact size of the pore because we don't have very sensitive measuring technique at this moment. But anyway, based on this, the pore size is 1 to 5 nanometers. And this one is almost same size pore developed in this micron-sized particle and nano-sized particles. And surface area of this micron size is around 540 square meter per gram. But the important one is this one. If you make nano-sized nanoporous particle, the final surface, internal and outside surface areas can reach up to 2,200 square meter per gram. This is very huge surface area of this nanoparticle. And this one, yes, we do some analysis on this, and just changing that ratio of the vapor material and catalysis can change the cross-drifting density. And this is the main effect to governing the final morphology and final surface areas. This is the total surface area goes function of the cross-drifting density. Cross-drifting changes from 0.6 to 0.9 is the total surface area varies from 1400 to the 2400. This is better TM picture of the micron size. Nano size, we don't have very good picture at this moment. But micron size, yes, this is this is the same SEM picture of that, and this is the 5,000, and this is the 20,000, and this is the 100,000. And from this main particle, and this is the part of this broken areas, and this is the actual surface of this the aerobic particles. And this one almost this is schematic diagram of these pictures, and here in this area, the black part of this area is this mass pore. And then this is the very small individual particle. Even in this individual particle has a very small pores. And this is AFF, result of that, the surface of that nano particles. And you can see here also another evidence. This one has an open pore developed on the surface of the particles. And this is one just physical property we managed to measure that. Using this kind of measurement, we actually measure the thermal conductivity of these porous particles, and we get in the vacuum system. Sample 1, if you remember, the sample 1 and sample 2 has a different solid content materials, and thermal conductivity of that is almost the same as the air. And even in the 76 Toll system, a little bit higher than this air, but is very comparable with this air, the thermal conductivity of this air. So this is another evidence to verify the particle well developed with the pore inside of that particles. The final one, this one is still undergoing research, but this is also a very important approach to use this supercritical system to develop some kind of pore. Not only just existing system, existing film, but also if you want to create some kind of a nano or micron structure during the casting of the film, this is a very useful tool to do that. So I'm going to show you that result. For that, we choose this kind of system. But this is conventional way of making the polyimide polymers. And we use this DMAC as a solvent because this one is soluble in the supercritical CO2. And we use this system because next one, we need to have some kind of this kind of CO2 generating combination system because we use this as a foam generating materials, foam generating side product. So we choose this diazocyanate and dianhydride in the DMAC solvents and making this make this polyimide precursor. Now this one you can easily apply on the system you make the casting film or whatever. So just to increase the temperature, now the imidization starts, and then slowly it creates the CO2 during this imidization process. And then use this as a foam generating material to create the foam inside of this casting tube. So this is the summary of the very simple process to create the porous polyimide. And this is the result. And this precursor film, this one, this is before the imidization. There's no foam generated. And then once it start to imidize, now the CO2 generate inside of this film and then create this form. And this is the result of the different size of this form depending on the pressure of the supercritical CO2. And let me tell you that we are not successfully to create a nano-sized pore at this moment. This one, the small size of this is around 900 nanometer size. So we are working on to generate a nano-sized form, but this is our so far we achieved to make this kind of about micron size forms in this polyimide. So let me just summarize my work. So you already know that by just changing your concept and applying our conventional chemical process can make very important job to create so-called nanomaterials. what I did apply in our system is just gathering some information and ideas and create some kind of process and then carry out the reaction. Of course, we choose some kind of model system at this moment, but this system can apply the general kind of system to create the nanostructure, nanoparticles, and nanoporous particles, whatever. So I just emphasize on chemical process is still very important process, and there's a lot of things you have to do a lot of research on. Thank you very much.